Let us discuss standard second order system and how is it represented and what are the parameters involved in second order system. Consider the g of s given by omega n square by two poles in the denominator, and assume that it is a unity feedback control system. Then the transfer function is given by omega n square by s square plus 2 zeta omega n s plus omega n square. This is the standard second order system transfer function, and this can be applied to any system. It may be an electrical system, mechanical system or thermal system. So there are two parameters that are involved in this transfer function. One is omega n. It is known as undamped natural frequency. Undamped natural frequency, radians per second, and the second one is zeta. It is known as damping ratio or damping constant. These two are the important parameters of second order system. What exactly undamped natural frequency and zeta? Their significance we will see with the help of one diagram. Now, if you see the denominator of this transfer function is known as characteristic equation or characteristic polynomial. It is given by a second order function it is. So it has two roots. It is known as characteristic polynomial. When you equate it to 0, it becomes characteristic equation. So the roots of this characteristic equation S1 and S2 is minus b minus 2 zeta omega n plus or minus under root of b square 4 zeta square omega n square minus 4 ac omega n square by 2a. So if you just see the two roots, if you simplify this, minus zeta omega n plus or minus j omega n under root 1 minus zeta square. So this imaginary part, it is actually minus zeta omega n plus or minus j omega d, where omega d is equal to omega n under root of 1 minus zeta square. So what exactly omega d here? Omega n, I said it is undamped natural frequency of the system. System may have some oscillations without any damping factor. That's why it is called undamped natural frequency. Whereas omega d is known as damped because damping factor or damping ratio existing in the equation. So it is known as damping or damped natural frequency. So if you compare this second order system with our electrical system, we have already discussed in the previous sections, it is actually given by 1 by LC and by S square plus R by L into S plus 1 by LC. So you can see that if you compare this standard second order system with our electrical system, omega n is given by 1 by root LC, undamped natural frequency. It depends on only L and C. Now the damping ratio So if you want to equate this S coefficient with this R by L, so 2 zeta omega n is equal to R by L, and substitute this omega n is equal to 1 by root LC into 2 zeta is equal to R by L. So if you solve this for zeta is equal to R by 2 under root C by L, means zeta is a damping ratio, it depends on RLC, whereas omega n is undamped natural frequency, it depends on only L and C. So the significance of zeta, if you remember or if you recall that such a second order electrical system without R, ignore resistance, only L and C are present, then you can actually see that when zeta is 0, that means R is 0, zeta is 0 when R is equal to 0, then it is called undamped system. That undamped system, if excited by some impulse input, if you see that what happens to the transfer function. So C of S by R of S is given by omega n square by S square. Zeta is 0, so this term is absent, so you have only S square plus omega n square. Now I would like to explain you the importance of zeta damping factor. It is a positive term. So if you excite this particular system now with zeta 0 by impulse input, say impulse input, that means R of S is equal to 1, then the C of S is given by the function itself because R of S is 1. So if you see the Laplace transform inverse for this to get a time response, C of t is nothing but sine omega n t. So imagine now the impulse input is a undesirable signal. It has very high magnitude and for very short duration. Such a signal, Laplace transform is 1, has a response of sine omega n t. You know that it is a sinusoidal signal having the frequency of omega n and that oscillations will continue. Means the response of impulse input this is 0, this is undesirable. Undesirable means signal that impulse response must decay as time approaches infinity. We say it is a stable system. So oscillations are sustained, magnitude is not changing but it has constant magnitude. So it says that impulse response with R equal to 0, that means zeta equal to 0, has sustained oscillations. If you introduce zeta, means R is not 0. With R is not 0 means zeta exists. Let us say this zeta between 0 and 1 means some value you have introduced. It should be greater than 0 but less than 1. If you introduce some resistance, now R is not 0, it has some value. Then if you substitute and solve for the roots, impulse response, if you see now, it will not be sustained oscillations, it will be like this. They are called damped oscillations. Damped oscillations means the magnitude of or the amplitude of the signal decays exponentially. So this is the advantage of damping coefficient or damping factor, that impulse response decays as early as possible if you provide some zeta. So that is nothing but damping ratio or damping constant significance. Now we discuss that let us vary the zeta damping ratio from 0 to 1 and equate it to 1, and then beyond 1, then what happens to the roots of this characteristic equation. That we should learn in this standard second order system. Now let us define the standard second order system in terms of damping ratio, because damping is the term which makes the roots of this characteristic equation to move. So when zeta is 0, that means there is no damping, so such a system is known as undamped. So when you substitute zeta equal to 0 here, the denominator becomes s square plus omega n square. So the roots of such equation s1 and s2 are plus or minus j omega n. Means if you see the s plane, this is s plane, this is the real axis sigma, this is imaginary part. Now when zeta is equal to 0, the roots of the characteristic equation, they lie exactly on j omega axis. This left hand portion or left half of the s plane is generally called as a stable region, and the right half of the portion is called unstable region. That means the closed loop poles of the system must lie in the left half of the s plane for the system to be stable. If any roots are lying on imaginary axis, means system reaches to the verge of instability. So beyond this imaginary axis, if any pole is in the right half, we say that system is unstable. So at this j omega n, this is minus j omega n, and this is undamped system. It is called undamped system because zeta equal to 0. Now you introduce zeta and you increase the zeta from 0 to 1. Then this pole move towards real axis, negative real axis, and this pole also moves in a circular fashion to this. So both the poles reaches the real axis when zeta equal to 1. Remember, the zeta is 0 here, undamped system, not a good system, but when you introduce zeta, the pole starts moving towards left. So suppose if you consider one particular point here, the value of zeta is greater than 0 but less than 1. So I say that zeta here lies between 0 and 1. Similarly, this pole comes here and the value of zeta is between 0 and 1. This is called underdamped system. Underdamped means damping is introduced. As you increase zeta further, when it is equal to 1, here, then both the roots have only real part, no imaginary part. So this is known as critically damped. This is known as critically damped. A system is said to be critically damped when zeta equal to 1. Both the roots lie on the same point on real axis without any imaginary part. Further increase of zeta. Remember that zeta I have given you for an electrical system, it is given by r by 2 under root of c by l. So keeping c and l fixed, I am varying r so that zeta is varying. So that roots, when you increase zeta beyond 1, one root, one pole will move towards origin. This is origin. One pole move towards origin and one pole move towards left of real axis, negative real axis. So one pole move this side and one pole move towards right for zeta greater than 1. That is called zeta greater than 1. Here also zeta greater than 1. Such a system is known as over-damped system. System is said to be over-damped. So, you have started from undamped, this is called undamped, and to underdamped, then critically damped, and then to the overdamped. It all depends on the value of zeta. But it is good that once you started increasing zeta beyond 0, the poles are in the left half only. But there is a difference. When poles are here having complex conjugate pair, response is for impulse input. If you see the impulse response in the case of underdamped system will have damped oscillations, means oscillations will die. Without any zeta, if you see the impulse response, sustained oscillations, not good. Sustained oscillations, impulse input is not a good system, means poles are at the verge of instability and it may become unstable anytime. So, further increase of zeta, what happens when it is critically damped, the impulse response, it takes more time to become 0. Further increase of zeta beyond 1, that impulse response, it takes still more time. We say over-damped system is most sluggish system. Most sluggish means it is not at all good system. It takes very long time to reach the desired output. So, in the case of over-damped system, if you excite a system with a step input, unit step input, then over-damped system means it takes more time to reach the steady state. That way we say it is a sluggish system. So, this is the movement of poles from zeta equal to 0, zeta less than 1, and then zeta equal to 1 and zeta greater than 1. So, this magnitude from here to here is omega n. Magnitude is omega n. Now, this one also, if you measure, it will be omega n only. So, the poles move in a circular fashion when you increase zeta. That is why it is a semicircle. You can see that the radius is omega n. Now, if you measure this distance, if you measure this one, this will be omega d, because you have introduced damping. Now, zeta is not 0. So, this magnitude is omega d and it is given by omega n under root of 1 minus zeta square. So, this is the magnitude. You have omega n under root of 1 minus zeta square. Then assume that this angle from negative real axis, say this is theta, it helps us in problems. So, if this is theta and you can see that this is a right angle triangle with a hypotenuse omega n, and this is omega n under root of 1 minus zeta square. Then if you measure this one, this will be zeta omega n. So, that right angle triangle, let me draw here, it has got some significance. This is omega n, this is omega n under root of 1 minus zeta square, and this is zeta omega n with an angle of theta. So, you can see in all the three parameters omega n is constant. So, you can say that this is theta, this is 1, this is 1 minus zeta square under root, this is zeta. A right angle triangle evolved from pole 0 diagram. Now, once you have understood that the poles are moving away from the imaginary axis when you are increasing zeta, and based on this zeta the systems are classified. I said undamped, underdamped, critically damped, and then overdamped. So, any system, as I said, there are two important things we should remember. One is the speed of response should be as quickly as possible. The response should reach the input, and it must be a stable system, means its impulse response must die as early as possible. So, here the most popular system is underdamped system, because underdamped system has got better response. So, we need to know that what is meant by better response in terms of certain time domain specifications. So, let us discuss now what are the time domain specifications that are required, useful to analyze the given system. This is only the explanation what happens to the roots of a second order system when zeta is increased. Now, we need to know what are the time domain specifications which will help us to analyze the system in a better way. So, as I indicated, we need to have certain parameters to judge the performance of any system. You might have studied in machines that efficiency and regulation, these are the two important parameters to know or to judge the machine is good or bad. Efficiency of the machine should be as high as possible, and regulation should be as low as possible. That way, even in the control system, I need to have certain parameters. With the help of them, I can analyze the system whether it is good or bad. So, for that reason, I consider again the standard second order system whose transfer function is in terms of two parameters. This one. Now, I need to excite this system by unit step input. Unit step input whose R of s is equal to 1 by s. Laplace transform of unit step is 1 by s. And let us assume again, always begin with case 1 that zeta equal to 0. The meaning of this, the system is undamped system. So, and with R of s 1 by s, the C of s become 1 by s into omega n square by s square plus omega n square. So, taking partial fractions into consideration and then get C of t, it is 1 by s minus s by s square plus omega n square. So, Laplace inverse of this, because I want to get the time response C of t. So, this is after getting into partial fractions. So, C of t now is 1 minus this Laplace inverse transform of this is cos omega n t. So, now this is the response you got for zeta equal to 0. It is called undamped system, and if you try to draw its waveform for impulse step input, because input is now unit step input 1 by s. So, with respect to time, the C of t. So, when this is 0, cos 0 is 1, so 1 minus 1 it is 0. So, it starts from 0, and then when this is 90, cos 90 is 0, so the output is 1, and when this is 180, because you started with this as 0, then 90, then 180. So when this is 0, the C of t will be 0, and when it is 90, cos 90 is 0, so it is 1. When it is 180, the response is 2. So it reaches to 2. It reaches to 2 by the time it is 180. So, and then it continues like this. It continues like this, and oscillations will be above 1 up to 2, and then below 1 up to 0. So between 0 and 2, the oscillations will continue, called sustained oscillations. Sustained oscillations means the two poles are at the verge of instability. So if you excite such a system by unit step input means 1 is the input. This 1 is R of t, unit step input. So the response C of t will never reach steady state value. It has oscillations, and that oscillations will be continued with a frequency of omega n. That omega n is nothing but undamped natural frequency. Means the oscillations of impulse response will be continued, and with a frequency of omega n, that is called undamped natural frequency. Now our intention is to see unit step response of a second order system, but not with zeta equal to 0, but we must go the most standard value of zeta is between 0 and 1, and very close, the best performance we will see that now will be between 0.4 to 0.7. This is the best figures of zeta damping ratio. So choose the value of RLC, because zeta is given by R by 2 under root C by L. So choose zeta such that it should lie between 0.4 and 0.7, so that the response will be better, speed of response as well as stability aspect. So we need to see the time domain specifications. Unless we know some parameters like efficiency and regulation, even time domain specifications are there to analyze the system whether it is good or bad. So we will discuss now time domain specifications of second order system for unit step input, and zeta value is between 0 and 1, means under damped system. Now let us consider the value of zeta for this second order system lies between 0 and 1. So this is called under damped system. And with unit step input means R of s is equal to 1 by s. So again, to the standard second order system, we have considered in terms of omega n and zeta excited by unit step input, and zeta is not 0. Then you will get C of t is equal to 1 minus e power minus zeta omega n t by under root of 1 minus zeta square sine omega dt plus theta. You get an expression for time response, and there is an exponential term involved, where you are aware already omega d is equal to damped natural frequency. When you introduce zeta, omega d comes into picture, whose value is given by omega n under root of 1 minus zeta square. And theta, I said in the right angle triangle we have discussed just before, theta is this angle. So this is 1, and this is zeta, and this is 1 minus zeta square. So if you see theta, this is nothing but tan inverse under root of 1 minus zeta square by zeta. So, these two are the factors that are existing in the time response C of t. Now, if you see here cos theta, of course you can get cos theta is equal to zeta, or theta is equal to cos inverse zeta, means angle depends on zeta. Angle depends on zeta. Angle is 90 when zeta is 0. So, that way this right angle triangle will help us in problems of time response. So, now these two are there, omega d and theta in the expression. So, there is an exponential term involved in the time response when you introduce zeta. So, this response will no longer exist now, because this is the response you got for zeta equal to 0. Now, you have introduced zeta some value, but of course less than 1. So, if you see the response, for unit step input again 1, the response will have like this. What is the difference between this waveform and this waveform? This has sustained oscillations, amplitude remains constant, but here the amplitude is exponentially decaying because there is a term that is involved here in the response, exponential term. So, it has damped oscillations. This is undamped oscillations and this is having damped oscillations. So, this is the response C of t for unit step input 1. So, this is good, this is not good. So, zeta having some value is a better system, because step response, you can see that finally this response is following the input R of S. It is taking some time, no doubt, but it is good that the oscillations are completely died out and the output is trying to follow the input R of S. This is called underdamped system. Now, let us take this signal and define the time domain specifications. So, say input is again R of t, it is unit step signal 1, and then the response will be like this. So, if you see this particular signal, I say that it is a underdamped response, and what are the various time domain specifications we need to learn from this. So, time domain specifications for this system. First one is delay time. Delay time is represented by Td. It is the time required for the response to reach 50% of the steady state output. So, 50%, this is the steady state value, finally 1. So, somewhere here 50%. So, this is known as delay time. Delay time is the time required for the response to reach 50% of the final value. Now, the second one is rise time. Rise time is represented by TR. Units are seconds. Rise time, it depends on the damping value. So, when I said it is underdamped system, it is the time required for the response to reach 100% of final value 100% of final value is known as rise time, this one. For the first time, so this is known as rise time. For underdamped system, we say that it should reach from 0 to 100% of the final value, because this is the final value the waveform is expected to stabilize. So, if it is a critically damped and over damped, the percentage is slightly different. So, it may be 5 to 95%, something like that. But our concentration is on underdamped system, and rise time is defined as time required for the response to reach 100% of final value from 0. Now, you can see that next definition, peak time. Peak time is represented by Tp, time required for the response to reach the first peak. It goes to the peak value. It goes to the peak value highest. So, time required for the response to reach the peak, Tp. Peak time is the time required for the response to reach the peak. Now, one more time that is required to be defined, settling time, represented by Ts. Required response, I mean the response must settle as time approaches infinity. However, how much time it takes for the response to reach steady state? We have discussed in the first order systems earlier that generally the response reaches steady state value in 4 to 5 time constants, where tau is the time constant. So, it may reach 4 to 5 time constants, the response may settle. So, the definition of settling time is time required for the response to reach and stay within the tolerance band. That tolerance band generally allowed is 2 to 5%. So, the output response can deviate plus or minus 5% in the steady state. So, settling time is time required for the response to reach and stay within the limits, that limits are 2 to 5%. Next, there is one definition, one parameter on y-axis, that is called peak overshoot. Peak overshoot is represented by m suffix p. It is a magnitude, the normalized difference from the reference, that is 1, to this peak. So, this is actually called peak overshoot. So, how much deviation in the response from steady state value? Highest difference from steady state value is this. So, peak overshoot is the magnitude, the normalized difference between the peak highest and the steady state value. Now, the last term that actually comes in the steady state part of the time response, that is called steady state error. Steady state error is represented by ESS. This steady state error means error in the steady state. Remember, out of 6, the first 5 parameters are in the transient part of the time response. When I call this entire one as a time response, it has got 2 parts. 2 parts means you can see that from here to here is transient response, because there are oscillations, okay, which are not permanent, and the response after these transients have died out is steady state response. So, out of these 6 parameters, first 5 are related to transient performance. When I say settling time, I feel good. For example, a system has settling time of 1 second or 2 seconds, say 2 seconds, but if I can make a settling time of 1 second or less than that 1 second, then I am designing a better system, because settling time means the response must reach the steady state value very quickly. Then we say it is a good system. In this case, the response will never reach the steady state because they are undamped oscillations and no question of steady state response at all. So this is good that if I have less settling time, less rise time, they are good indications of a system performance. So underdamped system is the excellent system for lesser rise time, lesser settling time, and so on. And peak overshoot also. Remember, peak overshoot is very high, no doubt, but that also should be within the limits. So all these parameters are called transient state parameters, and only sixth one is called steady state error, that comes in the steady state part of the system. So for any system, we need to know all these specifications to analyze. Now I would like to take the response C of t, and then I would like to give an expressions for all these parameters which will help us in solving the any given system. So as I mentioned, the time domain specifications of a second order system for this response, which we have got in the previous section. Now in this exponential term, as I said, these are exponential decay, and it is a sine term, so that there is a oscillation, and that oscillations are depends on omega d. That omega d means omega n under root of 1 minus zeta square. So that oscillations are not permanent, they are going to die as early as possible. So the delay time, I said, time required for the response to reach 50% of the final value. So equate this response to the 50%, means 0.5, and solve for t. Replace this t by td, that is delay time. You will get 1 plus 0.7 zeta by omega n. This is the formula used for delay time, and you get this delay time equating this whole function to 50%, means 0.5, and solve for t with t equal to td, and then you get this. Next, rise time. Rise time is the time required for this response to reach 100% of the final value for the first time. So this is rise time, 100% of the final value, means you must equate this function to 1, because the response value is 1, that is known as rise time. Equate this function to 1 and replace t by tr and solve for it. You will get pi minus theta by omega d. The next definition given was peak time. Peak time is the time required for the response to reach the first peak. So this is actually, generally peak time is given by n pi by omega d. So it is reaching the first peak, so n is equal to 1. So because the peak time definition is time required for the response to reach the first peak, so I write it is pi by omega d. Then what will be the time required for the response to reach the second peak? This is second peak, so that is given by 3 pi by omega d. So it is not 2 pi by omega d. Remember that between first peak and second peak there is something here that is known as valley point. first valley or peak undershoot. It is called first valley, this one, and this is first peak. So it is called overshoot because the response is beyond the steady state value, overshoot, and undershoot or valley because it is less than the desired value but it is going to lowest. That's why it is called first valley, it is called peak undershoot. So if the question is asked to find the time for the first valley, that first peak undershoot, then it is given by 2 pi by omega d. This is the time required for first valley point. This is the time required for the first peak, and this is the time required for the response for second peak. So that way you can remember n is equal to 1, 3, 5 for peak overshoots, and for peak undershoots, for valleys it will be 2 pi, 4 pi and so on. But the general formula, because we are more worried about the first peak, because system should withstand to that highest value. So we must take care of this peak overshoot should be within the limits. So whenever, generally what is the peak time means, you should understand by default it is time required for the response to reach the first peak, that is given by pi by omega d. And settling time. Now how to get the settling time? Settling time is the time required for the response to reach and stay within the limits. So you can see here these oscillations are responsible with this, and exponential decay is due to this. So that exponential decay or the amplitude of this sine term, you can see here this amplitude is becoming less and less, finally it comes to 0, but settling time is defined as 2 to 5% tolerance is allowed. 2 to 5% tolerance is allowed in the steady state. Means this amplitude E minus zeta omega n t by under root of 1 minus zeta square should be equal to 2 to 5%. That means 0.02 to 0.05. So if you take that, settling time will be 5 by zeta omega n if you do not take any tolerance, means 0% tolerance, and if you take 2% tolerance, then it will be 4 by zeta omega n. If you take 5% tolerance, it will be 3 by zeta omega n. Just see that settling time has got a very important significance, is that settling time means the response must stabilized, should reach the steady state. By that time the transients have to be died out. So it is taking 5 time constants, almost 5 time constants with 0% tolerance. That means I can say that the time constant of this second order system tau is 1 by zeta omega n. So the settling time is 5 times the time constants, because any system generally it takes 5 time constants time to reach the steady state value. So with 0% tolerance it is 5 by zeta omega n. Generally 2% tolerance is taken, so it is 4 by zeta omega n. So even in the problems when you are asked to solve the settling time with the information zeta and omega n supplied to you, you must take the default of 4 by zeta omega n if nothing is mentioned, because you must assume that 2% tolerance is allowed, and then you should use this formula. If he gives 0% tolerance, take this one. If he gives 5% tolerance, take 3 by zeta omega n and solve for settling time. Then another important parameter is peak overshoot. Peak overshoot is the normalized difference between highest peak and the steady state value 1. So this percentage, it is generally given in percentage. Peak overshoot, it is given by response at peak time minus response as time approaches infinity by response at infinity. So if you do this, you need to substitute peak time. I mean, what is the magnitude at peak time? So this is the magnitude, okay. And then C of infinity means it is the steady state response, it is 1. So what is this difference? That peak overshoot in terms of e power minus zeta phi under root of 1 minus zeta square. Peak overshoot is given by e power minus zeta phi by under root 1 minus zeta square. One important thing you must know, that in all the times, if you see delay time, rise time, peak time, settling time, there are both terms zeta and omega n, because even here also you know that rise time means pi minus theta, theta means this, and omega n or omega d is there, so you need to replace this omega d here. So in all the times depends on zeta as well as omega n, whereas peak overshoot alone, it doesn't depend on both zeta and omega n. See the expression for peak overshoot, it is given by e power minus zeta phi by this. So it depends only on zeta. So have proper zeta so that peak overshoot is not too much. Peak overshoot is not too much. So decide the zeta, and the most prominent value of zeta, I said, for even underdamped system, generally we call it is between 0 and 1, but the most dominating values are between 0.4 to 0.7. These are the best figures of zeta in any system to be designed or proposed.